Okay, so what we're going to be doing today is that we're going to be explaining some back propagation and then explaining something else. And so I've been watching, machine learning videos in the evening, and different people have different approaches to machine learning and like neural networks. And it makes you feel like it requires a lot of math. I don't really know if it requires a lot of math, but um, it could require a lot of math. But from what I'm seeing is that it's all just activation and then partial derivatives. It doesn't seem that hard, but I could be wrong. And there's also other people explaining it that just like skips all of the math and then kind of tells you more directly what it's doing. And there are pros and cons of it, and we're going to talk about back propagation this time. And so last time where we ended up on is that we have like a lot of these neurons, and then we have like layers, and then we have more layers, and then let's say we have these two. Let's just say we just have like 4 layers. And then we're going to output, for example, you get an input either 1 or it's either a 0, and we're trying to identify these two. Okay, so last time where we set off is that we give a lot of training, and then we kind of do gradient descent. But okay, I'm getting kind of confused because gradient descent. Wait, that's descent. That's not descent, but gradient descent and back propagation. Okay, I'm kind of failing to get the relationship between these two. What I have in mind right now is that gradient descent gives you kind of like a direction of where you need to go, and then back propagation tells you how much you need to go there. That's like the current state for me right now, but I could be wrong. So gradient descent gives you a giant matrix, like C, delta C. It gives you a giant matrix, and then back propagation kind of tells you how much you need to move it. And so from like a very intuitive way, back propagation is just we calculated the cost for everything is that, for example, the probability of this is 0.7, is 0.6, and then this is probably a horrible data set, but we're going to give that this is going to be 0, this is going to be 1, and then we also know that this is going to be 1, this is going to be 0, so we're going to calculate it like this: 1/2 over times 0.7 minus 1 squared plus 0.6 minus 0 squared. Yeah, it's going to be that. And so once we have that, this is our kind of cost function. I'm trying to minimize the cost function. And so what the cost function is consisting of is that this is going to be kind of consisted of the weights made from these. So like the activation function, and then it's going to be weights. It's going to be like say weight 1 A1 plus weight 2 A2, and then it's going to be plus a bias B1. This is going to be the thing for him, which is going to give us that. And then the other side is still going to be the same. And so this is going to be that. And for this neuron, it's just going to be all of this. So this is a ton of calculation. This is why we kind of use matrix calculation, because matrix calculation has been super optimized for like GPUs and stuff. But from my point of view is that for every neuron, this is like the kind of last step. For every neuron is just substituting it for like that. We can substitute it for something else. It's going to get more and more complicated, I think, over time, but it's gonna be pretty good. Yeah, it's gonna be pretty good. And so once we have that, we kind of want to we want to know, like, there are going to be some factors that contribute more to the there are going to be some factors that that attribute more to the cost function, because some okay the way I saw other people explain it by Common Luke is that think about the end result. Let's erase all of this so I don't need to redraw it. Let's think about the end result. So the end result is going to be a dish. It's going to be a dish. And so for all of these are just going to be chefs. And then all of the chefs are kind of adding their secret sauce, their ingredient to the dish. And so there are like main chefs that add like important stuff. And there are also like, I wouldn't call them side chefs, but not that important chefs. And so, for example, maybe one chef controls the salt, and then he's responsible for like a huge part of how the dish would taste, because it can either be super salty or like very plain, and so he has to get it right. So backpropagation does right that. So it figures out, okay, you're contributing a lot to the dish, and so I'm going to change you more so I can actually get a better result. And so this is using partial derivatives that I can't really explain right now because it's math. And another thing is that how much you want to change the thing by. And so you want to change it. Wait, this kind of goes against the gradient descent and backpropagation. Okay, I need to figure out the connection between gradient descent and backpropagation. And then we're going ahead of this, and then let me see. So once we have this, and we also kind of need like a learning rate. And so learning rate is that once you have the backpropagation, you're kind of going to change. You're going to change the like. For example, you're here. The next step you're going to be here. This is the learning rate. So this is how much you want to change because you're trying to find the local minimum. And then I probably have gradient descent and backpropagation all messed up. But learning rate is how much you want to move by to get to the next place. And so ideally, you want, if the slope is really, really steep, you want the learning rate to be higher. So you can jump like boom. You can jump like that. And then you can jump like that. And then that. And then so once you want the learning slope to be like very, very small, you want the learning rate to kind of be smaller, because you don't want to overshoot it and then be just jumping all over the place around this local minimum. You want to get the local minimum. And so once we have that, we're basically getting all of the weights and stuff. And so it's actually pretty amazing how like machine actually learn all of these stuff. Like it's learning with like a huge, very complicated thing. And it like props to the first guy to discover all of this. And I'm still kind of like a noob at machine learning. This is why tomorrow I'm gonna try some PyTorch. And then because PyTorch is based on Python, and then it's like a library, it shouldn't be that hard, because a lot of people use it, and it shouldn't be that hard because it's written in Python. And so this is like machine learning. I haven't coded anything yet, but we're gonna try that. And so part 2 has basically nothing to do with machine learning. It's basically telling you that some things I've been looking forward to. No, not looking forward to, but kind of studying. And so the first one would be that how the computer reads JPEG and then PNG. And so, or what's the difference between JPEG, and then this is a normal photo, and then like a medical photo, like DICOM. I don't know what that stands for, but this is 2D, and this is 3D, and then this is red, green, blue. This is just like values, like physical physical values like density. This is going to be density, and then there's also going to be a metadata, I think. Is it called metadata? Yeah, it's called metadata. Metadata. Data. This is going to be none. This is going to be metadata. Okay, I'll explain what all of these do. And so this is 3D because we remember that CT is basically surrounding you and then doing a lot of x-rays. And then although it's 3D, it's actually, you're going to give it 4 inputs. The first one is going to be, hold up. The first one is going to be how many channels there are, which is not that important if we're just considering all this. And it's going to be X, Y, Z. And then it's also important to note that the 3D actually mean like 3D, like cubes in the air, cubes, instead of like dots. Because if you think about it, a photo with dots is just not usable, because you kind of want to locate it, and it's like a space, it's not a dot, right? And so how the computer loads all of these images, they just kind of so you kind of use like tools in Python, but what the computer does is that it converts like a photo to something that a computer can read, which is called a tensor, which I have basically no idea what it's doing, but this is kind of like the action. I need to figure this out, and then it converts it based on the suffixes, or like for example, if it's like JPG, then it's just going to use another module. If it's like from NII, it's going to use a different module. Yes. And so there's also going to be metadata, because you kind of need metadata, because for example, like a CT, you need to know where you're scanning, like which part of the you kind of need to know like which direction you're scanning in, and then like for example, if you're scanning it counterclockwise or clockwise, and then how much each cube is, because maybe some cubes are different, and how you transcribe into actual real values. These are all things that you need to kind of consider when you're getting the metadata. So the metadata is really what's getting these values to actual values in real life. And yeah, that's basically it.